the project I'm working on is infant baby monitor project. The baby monitor market is like a growing industry, and this particular product shares a small percentage in the baby monitor industry. It's not a movement monitor. It's not a regular monitor. And right now, all the current regular monitors are going towards HD video and two-way audio streaming and stuff like that. But the last thing a parent needs to know about their infant is if the baby is sleeping or just awake or not breathing or just roll over from the bed. So keeping that in mind, we try to come up with a design, come up with a new monitor design, and we got our motivation for doing this from disease that's called SIDS, sudden infant death syndrome, which is an unexpected sudden death of a child under age 1, in which an autopsy does not show the explainable cause of death. So having a monitor to look for the breathing levels of the baby and not just streaming an HD video to the parent was a solution. Even though it's not a life-saving device, it's just a monitoring device, it will help the parent to know if their baby is breathing or not. And these are some statistics about the SIDS, and it accounts for the 20% of infant mortality rate. And there's nothing we could do about it because there's no medical explanation for SIDS. That the only way we can prevent it from giving medical attention to the baby as when we see the baby does not breathe for more than 15 seconds. So the goal of this project was trying to look for the baby's breathing levels and alerting the parent if there's an unusual breathing activity takes place. So we came up with a concept model that uses an air mattress. This is just a prototype. It's not the real bed that we are going to use. And it will be hooked up to a base unit, and there will be a pressure sensor inside the base unit that will constantly monitor the pressure variations, and it will run an algorithm, and it will send the status. It will update status like 20 times in a second to a receiver unit, which will be placed in the parent's bedroom. And using the pressure sensor to look for the breathing activity was a completely new idea. We looked on the market, and there was only one manufacturer who does breathing monitoring, which was Angel Care. They use a piezoelectric pad put under the bed, and the problem was many parents don't want to see their infant's crib running wires into it, and it will just add more concerns for them. So we want to have a monitoring method that does not uses any electrical contacts, electrical leads running into the crib. So the first thing we gotta find was the right pressure sensor. And if you think about how a baby breathes while he's sleeping, that's a really minute change in the pressure. And we gotta have a pressure sensor that's sensitive enough to pick up that small changes from the pressure sensor, from the air mattress. So we came up with this requirements. We were looking for a pressure sensor with at least 0.01 psi, and it operates between 0 to 14 psi because for a child under age 1, the maximum weight, it will be around 16 or 14 pounds. So so the pressure sensor can operate within that range with the added pressure on the air mattress. And I was preferring a digital sensor because it's more easier to work with on the controller. And conversion time, that was another thing, because we need to update the status like at least 20 times a second to the receiver unit, and the conversion, the pressure conversion from analog to digital should be really fast. The microcontroller needs to get the pressure data really quickly in order to calculate the algorithm, and for this product, time is everything. And yeah, and an operating voltage would be 2.8 or 5 volts. So these are some few sensors that we tested before for this particular application. And this one is from Freescale Motorola, and it's actually an analog sensor. It had a lot of sensitivity levels that meet the standards, but the problem is there was a lot of noise coming with it, and the low signal to noise ratio. So, and there was no way to filter out the noise because it's gonna damn the sensitivity of the pressure sensor. So we rejected that, and we got another one from China. It's a Speaker 0S. It's a digital sensor which uses I2C digital interface and gives a 16-bit data. But as I discussed earlier, it wasn't fast enough. The piezoelectric material inside taking too long to relax after putting pressure on it. So we rejected that, and finally we got our guy. This is the Yamaha 5536, manufactured by Measurement Specialties. It's a pretty old sensor. It's a 4-year-old sensor, right? And at that time, it was manufactured by Industherma in Switzerland. Right now, they own, an American company owns this company, and it offered a lot of things that we wanted for this project, like pressure ranges between -400 to 1000 millibar, which is like 0 to 15 psi, and 0.1 millibar solution, that's 0.001 psi. So if you think about how much is a 1 psi, you can just imagine how small a 0.001 psi will be. So the sensor is able to give that small change in the pressure, and it's a factory calibrated, and uses a SPI interface, 3-wire SPI interface, and uses a low voltage and low power. So this is the internal circuitry. So this is the sensor we have right here. It's a piezoelectric material, and we put the pressure on this material, and we get the voltage out from this material, which converts to a 16-bit digital out. So working with this particular sensor to get the data was really pain, because it was using the bit bang method. It was not using the conventional SPI interface where you just send a 8-bit data byte, and it gives you back some the information that we want. But this particular interface uses 3-bit start bytes and 4-bit setup bytes, and 3 bits for stop bytes, which is low. So I had to bit bang and stop the clock signal after 17 clocks. So after 33 milliseconds, the sensor will start to send out the 16-bit data with the MSB at first. And I was running the sensor at 250 kilohertz, and it was pretty fast enough. for our application. And the next section is the microcontroller. So the microcontroller has to support the SPI interface, and I was going to use some timers and for frequency generation and signal processing, because I'm going to use some interrupts. So the microcontroller should have at least 2-3 timers inside it, and the CPU frequency must be greater than 32 kilohertz, because the sensor needs to be clocked with 32 kilohertz. So I decided to generate that frequency from the microcontroller itself. And 8 kilobytes of flash, USR, which I use to communicate with the RF modules, and pulse width modulation, which I just use to mimic the breathing activity of the baby when the baby is breathing. So when the base unit sends out the signal, like when the baby is breathing, the venality starts to go dim and go up. So I need a pulse width modulation also. So this is the chip I use, 80 mega 32L, which is pretty high for a high standard for this particular application. But this particular chip can run at higher speed, like 60 megahertz with low power, and it got 2 8-bit timers and 16-bit timers. So I would like to go with this instead of going with the 80 mega 8, which has less GPIOs and less flash, and it's going to be less expensive. For development, I decided to go with this because I need to test other sensors also. So yeah, it just shows all the properties of the microcontroller. And the compiler I used was Atmos Studio 6, which is powered by Microsoft Visual Studio. And the language I used to program was C and C++. And the programmer, which is AVR Pocket Programmer, that is a CSP interface to, basically SPI, another SPI interface to program the data into the flash. Now, on hardware design, what happens is the microcontroller gets the data from the pressure sensor at 250 kilohertz speed, and it does some algorithm to calculate the pressure, to process the signal and send out some 5 different status bytes to the receiver unit, which is right here, through the RF module. And the receiver unit decodes their statuses and puts the output into an LCD display. And we also use a buzzer to alert the parent if anything goes wrong. So this is just a high-level hardware design for the oral circuit. The base unit uses a 5-volt DC power jack and to a wall adapter, and the receiver units, which is this one right here, is a 9-volt battery inside, a transistor battery. It's regulated by a voltage regulator. And for RF communication, I use an 8 data byte frame with a 1-stop bit, and the LCD display is 4-bit interface to just shorten the number of wires I have. So this is just the basic schematic for the RF circuit. And this one right here is the sensor interface circuit. I had to eliminate the noise signal coming out from the DC power supply, because the noise signal when there's noise signal in the DC power supply, the microcontroller will interpret that as a change in pressure. So I added a 47 microfarad counter capacitor to regulate that power supply. And next we go to signal processing. For this particular application, it's hard to get a in-fan all the time when we have a code ready to test on. So I just basically made a air bag filled with air and connected to the base unit, and the air bag attached to the seat where I was working, and it was basically getting my breathing levels. So
A little bit too big for an infant.
yeah, that's right. So the one you see right here, when I was just not moving at all, just breathing at a without exerting more pressure, just breathing at a normal rate. So this is the pressure out from the sensor. I used MATLAB to plot this data, and this one right here is when I just make random movements with my hands. The pressure sometimes drops a lot, and it goes up high sometimes. And the one you see right here is when I kept my breathing when I stopped breathing for a while, and the pressure sensor was able to detect that change in pressure inside the inside that air bag, and I decided to make these three different states as the basic status for the base unit. So the goal of signal processing will be trying to identify these three different states. So I use timer interrupts to identify the change in pressure. So each vertical lines you see right here is a ISR timer interrupt at 1 second rate, and at each second it samples the data from the pressure sensor and stores in a variable, and in the next second, when the control comes over to the ISR next time, it samples the pressure data to another variable, sample 2, and it's just basically subtract the difference and finds the difference between these two pressure values. So as you see right here, it gets the difference, the change in pressure. The red dots represent the pressure value at when the ISR or the inter-service has been fired, and captures the data into a global variable which is accessible to all the programs and functions. So it shows you the difference. When I stop breathing, the difference gets low, and it's almost equal. And I made another graph which is with on bottom level I'm showing that difference level that I'm getting from the MATLAB, that I'm getting from the sensor. And as you see right here, when I'm breathing at a constant rate, I'm getting the difference more than 6 or 6.5. So, and when I'm just making random movements, this graph represents the random movements I was making, and I was getting some peaks at some point up to like 120, and sometimes there's nothing. So, and this one right here represents when there's no movement, when there's no breathing goes on, and as you can see right here, it has a certain delay for the MATLAB to plot the data, and after I stop breathing, the difference just is always below 5 or 6. So with that, with that limit, we could adjust the sensitivity level of the device. So let's say if a baby which is around 6 pounds, and he or she is not going to have that much pressure, not going to put that much pressure on it. So we could adjust the sensitivity level using a control knob, which I decided not to put in there. So right now I'm trying to figure out the weight of a baby from the pressure, measuring the pressure, and the program set the sensitivity level by itself. So yeah, moving on. As the microcontroller sets the bar and see the difference, if it sees the difference goes down that sensitivity limit, it sends status bytes, and there's 5 different status bytes, which the one I just mentioned is here, is the 4th one, no movement from baby detected, which is, so as soon as the microcontroller sees there's no movement detected, it starts to send the status byte, and when the baby starts to move, it just like the baby's awake. So, and I'm also working on a new algorithm to figure out if the baby is on sleeping or just awake, just by storing all the past 10 values of difference and storing it in a stack. And if we add all that, we are going to get a value between a particular range. So the microcontroller can say, yes, the baby is on sleeping, and the waves represent a sleeping state. So I was using the RF circuit, 350 megahertz carrier wave with 300 bit per second, and it offers maximum of 300 feet, which is it's also ASK modulation, amplitude shift keying, so it modulates the amplitude of the 350 megahertz carrier wave to send these status bytes. So at the receiver level, everything that receiver gets is the status bytes, and I programmed it in a way that the LCD shows the output whenever the receiver unit receives status byte, except in this case when no movement from the baby is detected. As soon as the receiver unit gets this particular status, the receiver unit starts a timer of 1 second, and the ISR keeps coming back at 1 second to check if there's any change in the status. So this is the ISR interrupt service routine in the flowchart. So it always looks, in every 1 second it comes from the main, it interrupts the main program and checks for statuses, and if the status doesn't change, it also starts the counter, and if the counter went more than 11 seconds, I mean, if you come to an ISR program which fires at every 1 second, and if you have a counter that's incremented up to 11, that means it's the 11th second. So if the counter is more than 11 seconds, the ISR initiates an alert action that sends pulses to the buzzer and the red LED. So yeah, that's all about the alert action. And there's like a few checking inside the ISR to prevent it from a false alarm. So it checks the status every time its values in a ISR, and if the status change to something like baby start to breathe again within that 11-second frame. The ISR cancel the timer and the counter, and reset the timer and go back to the main program and start doing that all over again. So the results. Was a nice experience working with SPI interface and all other embedded systems, and we were able to get a reduced false alarm because the sensor was so high sensitive, and it was able to get the almost every data accurately compared to the other sensors we just tested. And one of the main advantages of this particular system, which I think, is monitoring of the breathing activity without any optical contacts. And there was some bad results we got from this project. Like the battery life of the receiver unit was way below because we were using the battery to lit up the LCD screen all the time, so it was taking a lot of juice from the battery. And the RF module that I use is designed to work with an antenna, and we don't have an antenna right now. We just have a wire antenna wrapped around in the box, so the signals is kind of weak after you move over 150, so you get broken signals. And there was also an issue with the frequency shift because the receiver unit works with the ISRs, and the base unit sends the status without any delay, like all the time. So the receiver unit had a issue with the synchronizing these bits. Even though there was a synchronization bit, I sent synchronization byte like 10101 all the time before I sent out a byte. So there was also a frequency shift issue. And the power supply, I use a 5-volt DC jack, which I got from another device, to power the base unit. And if there's if it's not a clean supply, there's going to have a lot of noise, and the sensor is going to give more noise output to the microcontroller, which makes the detection more hard. So we decided to put all the circuits and everything from breadboard to a small enclosure, so it will be nice to look at and it will be easy to work with. So the one you see right here is the receiver unit enclosure, and this is the base unit enclosure. It's going to have a switch right here and a green LED indicating the base unit is turned on, and it started to get the data from pressure sensor and able to send over to receiver. Since it was just a one-way communication, there was no, I was not able to get an acknowledgement in the back. So just sending the status signals into the air, and the receiver unit is going to have a LCD display and switch and a buzzer and a green LED to indicate that the device is on, and the green LED will start to mimic a breathing activity when the base unit tells the baby is in motion or sleeping, and the red LED, which I use to indicate when there's no movement detected from the pad more than 11 seconds, which is like a danger limit. Like a normal baby can stop breathing for 9 seconds, which was unknown to me. I mean, which is a normal thing for an infant to do, to stop breathing for 9 seconds. And so we decided to set the 11-second time limit. So we'll think of this is just the phase 1, so we can move forward with a lot of more improvements in the future, like two-way audio streaming, so that parents can listen to their baby. If the baby starts to cry, the microcontroller starts the microphone and the speaker at the receiver unit, and the customized pressure sensor for very more accuracy, and the Bluetooth support, so that a dedicated Android app can update the notification or to the notification in the notification bar. Let's say the baby is sleeping or is baby awake, and improve user interface. Also, I was thinking about using this particular monitoring technique for adults to monitor their breathing activity, because as you saw just right here, like it was able to pick up my breathing levels at so much accurately. So but only use it for adults in like hospital environments, which there we don't have to put electrical or some other sensors around the nostrils. So that's all about my project. I want to thank Dr. Waziri for providing all the support. And the enclosure, the box, he got it from Japan. And Mr. Isaacs, he came up with the original concept for this particular product, and he helped me to make the box enclosure and get the sensors, and also help I could expert. And David Ezekiel, he was so generous. He is the vice president of Servoflow Corporation, which is a supplier of the measurement specialties, and he was so generous enough to give us 6 free samples of the EMS 5536, which I think is pretty expensive in the market. And Ton Lava, I was like always interfering with, like asking for tools and components, and it was so nice with me to get the stuff from downstairs in the case. So I want to thank him and all the engineering faculties and all the friends who just helped me to go through this project and borrow some resistors or capacitors or some MOSFETs. So these are the references I used for preparing the project report and this particular slide. And I want to invite Mr. Isaacs to talk a little bit more about the marketing and manufacturing and his views on the future of the product. So I will set up the demonstration while he's doing this.
Hi, Richard Isaacs. At Isaacs Design and Development, we specialize in toy and infant care product development. And it was a terrific opportunity to work with SUNY Paltz on this project. And I wanted to thank the professor for putting us together. So thank you, Professor Waziri. And the particular project here involving infant care monitoring is an area that has lots of manufacturers involved in trying to provide different monitoring solutions for parents. And so as Alwin had mentioned, this particular device allows you to have additional monitoring capability without having electronic fields around the child, and to also provide more information to the parents, especially of those children that are 12 months and under. We normally work with companies like Mattel, Hasbro, Fisher-Price, and in this particular area, our manufacturing partner in Hong Kong is a supplier to one of the largest infant monitor companies, and we hope to have this in production once some of the other engineering, biomechanical questions are answered, especially with the pad. Right now, the pad was developed to give Alwin something to work with so he can do his electronic development. But that's more of a biomechanical engineering project there to create a pad that is more flat, more comfortable for the child, in addition to providing the right amount of impulse and air pressure to Alwin's electronic system. The product is very close. After Alwin spending a lot of time in all manner of different areas, aside from the electronic engineering aspects, there's kinesiology questions, how children and young infants especially, generate impulses by the way they breathe. And so he had done lots of extensive research, and I applaud him for his efforts in, delving deep into areas that were not essentially related to the electronic challenges, but also to the biomechanical issues related to how to maximize getting sensory data off of a child that breathes and moves in almost slightly imperceptible ways. And so we look forward to being able to complete the development in the next month or two, and hopefully in the springtime get into production. If any of you are interested in the opportunities or what might be out there for electronic engineers in the toy and infant care industries, please contact the professor, and perhaps I can then be contacted and I can talk to you about what opportunities are there. I think it's an area ripe for more electronic development as technology progresses forward. So I want to again thank the professor, the university, and also to Alwin for all of his work on this project.
So just set up a small demonstration right here. So the base unit is going to activate only when it detects a particular amount of pressure. When the pressure inside the air matters goes beyond a threshold limit. Otherwise, the base unit is going to show like there's no baby on the pad. So it helps the parent not to worry more about the base unit and the other statistics, 10 off or 10 off and 10 on, things like that. So when there's a baby on the top, the device changes the status to like baby's awake, and green LED starts to mimic that breathing activity. You guys see right here. So if let me see if I can try keeping it steady for like 6 seconds. Right now I put the time limit to 6 seconds. That's so that I can get a faster alert. Which is so hard to do it, by the way, because it's like sensor is so sensitive. It can't even take your pulse change from sensor. And also, I was getting a lot of noise from these particular adapters, so yeah. So that's you just see. I mean, when there's no movement, it came from the pad. It sends the status signal, and the receiver unit starts the timer. Right now it's 6 seconds, and it gives an output in buzzer and a red LED. So that's all. So that's the basic working of the infant baby monitor. So you don't got any questions?
Do you have an estimate of the cost?
Yeah, right now,
I understand that a lot of things are not in the production level, but as far as the electronic,
yeah. Right now, all the electronic components that we have, except the bed, all the microcontroller and the pressure sensor, it adds up to $50. But when it goes to manufacturing, you can get this product as low as $20 because you don't need that much powerful microcontroller, which is 80 mega 32. You don't need that much flash space, and you could just use a 80 tiny or 4 kilobits of flash space. A cheaper microcontroller to use for this particular application, and while manufacturing, while mass production, we could get this piece to around $25-30, I think, which is way below the current baby monitors in the market, which is priced around like $150 with a HD streaming, two-way audio, which does not give any information about the baby's breathing or not. So
how much is the sensor, the pressure sensor?
pressure sensor, the one we have right now, it's a 4-year-old one. There's actually a new edition of it. The factory just stopped manufacturing it because of some problems, right? So how much?
There's a new
Yeah.
generation sensor. That current sensor is $21.
Yeah.
Yes, in low volume.
Yeah, but that's the most expensive.
Yeah, most expensive. But we can reduce that cost in mass production.
Yeah, and this is the only sensor we found in the market which is so sensitive enough to do the job. So,
The sensor supplier is currently developing a new generation sensor that will have the same sensitivity as this one at a fraction of the price.
So this one relies on air methods, right?
Yes.
So could perhaps, but the unit just responds if there is a problem. It's just a warning, correct?
It's a warning.
As opposed to perhaps could feed back into the air mattress to, change the pressure and get the baby to move a bit, perhaps.
Well, that encroaches into an area that is considered a medical device.
I see.
So there are devices like that that help stimulate additional breathing in a child in say, a neonatal intensive care ward. But when there's a fine line what the FDA will allow in the consumer product area that would then otherwise become claims you have to make to the parent or to the industry that once you go over this threshold, it becomes a medical device and it cannot be a consumer device.
As far as the battery, I just don't understand why you cannot use the signal that you receive as an alarm to set a switch up, to turn your monitor on at that time, instead of having it on the whole time, and so that could address the problem of your battery situation. Because you already have the mechanism in place, so just use it directly as setting off the switch.
Yeah, we just need a MOSFET switch to turn off the LCD backlight.
Exactly.
The problem was there was much time to do that because we just got the.
No, I understand.
Yeah.
As a future,
The final production piece won't have the LCD screen. Most of the reason for the LCD screen is for development purposes to see what the condition is. So there's costs involved there.
And that takes most of the power.
And it takes a lot of power. But as you can imagine, a parent doesn't need often really the micro information of what's really happening. They just need to know you need to get into the bedroom.
Yeah.
Makes sense, yeah. Good job.
Okay, very good.